Okay, good morning everyone. Let's get started. So today we're going to move on. In the previous couple weeks we've been talking about the application layer, and today we're going to move on to talk about the transport layer. So now we've been talking about this concept of layers for a while, and you haven't officially been introduced to the entire network stack. So let's go over that to frame the concept of the transport layer, okay? So far your view of the network is you know what network applications are. So you know about the application layer. And in the very first day of class, Professor Keshav gave you an overview of the physical layer. Now you don't know the details yet of the physical layer, but you know what it looks like. Right? So can someone give me an example of an internet application? So we have email. What else? HTTP, heard. SSH. One time we talked about peer-to-peer, and so on. So, and there's others like DNS as well, and there's many more as well. All right, so you have a good idea of what the application layer looks like, and you have a reasonable view of what the physical layer looks like. You know that it looks like something like you have your home computer. It's connected by a wire to your home router, which is then connected to your access ISP, which connects to the core. And so you have some idea that these are these hardware devices, and that the physical layer, that the goal of the physical layer is to tell these devices how to communicate with each other. So it tells you how to communicate over a medium, such as your medium can be air, for things like wireless transmissions. Air can be copper wires, or it can also be fiber optics. All right, so these are the sort of physical layer technologies that actually, when put together, make up the internet. But in between here, we have this stack that makes it easier for us to write applications on top of the physical layer. If we only had the physical layer and the application layer, anytime you wanted to write an application to access the internet, you would have to write all this functionality yourself. You would have to write, like put these bytes on the wire, encode it in this way. If you have a wireless transceiver, that means you run these radio waves and so on. So it'd be extremely difficult to directly write to the physical layer. Okay, so to make things easier and to also motivate the design of the internet and keep things clean, we've broken the internet down into these 5 primary layers. Many models use 7 layers, but we're taking a sort of simplified view in this class, so there's only 5 layers. And so in this class we've been working top down, so you know about the application layer now, and next we're moving to the next layer down, which is the transport layer. Okay. I will define the functionality of the transport layer momentarily, but before I do, let me just fill in these remaining 2 blanks. So below the transport layer, we have the network layer, and below that we have the link layer. All right. So as we move down, once we have applications, we can define now the goal of the transport layer. And so the goal of the transport layer is to provide seamless communication between applications. So the way I'm going to phrase this is that it provides logical, which I'll define in just a minute, logical communication between applications. All right. So what do I mean by logical? By logical, I mean that the applications actually think that they're directly connected to each other. So if we have a logical connection between applications, it doesn't matter where these applications are running. They think that they're directly connected to each other. So suppose that you and I have some application talking to each other on our laptops. From the point of view of the application, it doesn't matter if our laptops are sitting right next to each other, plugged into each other with some sort of cable, or if I'm here at school using the wireless internet here at school, and you're at home using your cable modem. From the application's point of view, and the code you write, the functionality behaves exactly the same. Last time you talked about socket programming, and so these sockets enable you to simply write the same code, and then wherever your clients are located, the other layers can handle getting there and handle the differences between, suppose if someone's on a Wi-Fi network versus like a cable network versus something like DSL, then the actual physical bytes and the way you modulate the signals and so on is different. However, the physical layer handles that, and the other layers on top of that add functionality to make it easy to write applications. So let's move on to just give a brief overview of the network layer, just so you understand what it does, and also the link layer. So the network layer is responsible for routing datagrams. And in particular, it's responsible for routing these between networks. Now, by routing, I just mean that it instructs these datagrams, which this is the fancy name for the network layer packets. All right, so there's lots of jargon here, I know, but these are just segments of data encapsulated in a packet. And so the network layer is responsible for saying, oh, okay, this packet is destined for this IP address. I know how to get there, and I can forward you along a path to there. All right. Then the link layer is responsible for communication between nodes on the same link. And what I mean by this is if we have a link like this, then the link layer handles the behavior of these two endpoints, right? You may need to if this is, for instance, suppose that this is a Wi-Fi access point, and this is an internet router, then there needs to be some sort of conversion between the native format of this Wi-Fi router and this internet IP router, all right? So the link layer handles that functionality, and then the physical layer handles the actual transmission of the data across the physical medium. Okay, so in the coming weeks, you will learn much more about the network, link, and physical layers, and the goal for the next 2 weeks is to give you the fundamentals of the transport layer. And so that's what we're going to talk about today. First, we'll go over some more of the concepts behind the transport layer, then talk about this thing multiplexing, demultiplexing, and then introduce you to one transport layer protocol. And this is the simplest transport layer protocol. It's called UDP. Now, to give you an idea of what the transport layer does, now you know that it provides this logical communication between applications, but let me give you just a sort of analogy to hopefully make it a little more concrete in your minds what it's supposed to do. So suppose we have two houses, and suppose that this house is in Vancouver, and another house here in KW. All right, and there's a bunch of cousins that live in each of these houses. So each house has 12 kids. So there's 12 children in each house. And these kids are very prolific letter writers. And each of them writes each kid in the other household 1 letter a month. So that means that between these two houses, they're exchanging 144 emails, or sorry, mail, like actual letters per month. All right. So now, what are the applications in this analogy? Well, the applications are the children themselves. We'll say that these kids are all cousins of each other. So the kids themselves are the applications. Right? And now they need some sort of transport layer protocol to ensure the end-to-end delivery of their letters to each other. And so we'll just define a transport layer protocol. And for that, we're going to say that the oldest child in each household will be responsible for collecting the letters from the other kids and then taking them out and putting them in the mailbox each week. All right, so we have a mailbox, and the oldest child, just to make this a little more concrete, let's give them a name. Let's say Anne here in Vancouver and Bill in KW. So these, Anne and Bill, are our transport layer protocols. And their responsibility is just to simply, when they're sending messages, they collect the messages from all the children and then take them out to the mailbox. So that's what they do when they are sending, and then when they're receiving, when they receive messages, their behavior is to collect all messages, collect the mail from the mailbox, and then they do the opposite of that, and so they simply hand them out to the other kids. Let's just say hand letters out. All right. So now, does anybody know what the network layer would be in this analogy? So the answer is the mail service. And so let's just say Canada Post, for instance. And this is our network layer. Now you can see that in the internet, the network layer is responsible for routing between networks. And that's exactly, and knowing how to route messages to their proper destination. And that's exactly what Canada Post does. If you give it an address, a letter with, a sufficient amount of postage and an address, then they will take it from any destination in the world and deliver it to the endpoint. And that's exactly what the network layer does. Okay? So then, does anybody know what the link layer would be here? Okay, so the answer is the mailman. So, yeah, it would be, so the mailman is one link layer protocol that would be used here. So you can think from the postal, let's draw it as a cloud, similar to the way we do internet things. Let's say this is the postal, that's like the sorting and so on center. So let's just say the postal center. Then the mailman is responsible for this link. So he's responsible for the connection from this postal distribution center to your mailbox, right? So this is one link layer protocol that's used here. Draw these. And then another one would be, for example, if from Vancouver to KW, if the mail was sent via an airplane. This could be another one. Although, sorry, let me not actually write airplane, let me write flight. Because there's a whole set of protocols and customs and so on associated with the flight. For instance, the mail may have to be x-rayed and so on before you put it on the flight. So then all that together is the link layer protocol of the flight. And then again, here we have another mailman who actually delivers it to your mailbox, okay? And then the physical layer, in this case, can anyone tell me what the physical layer would be? The actual trucks. And the planes themselves. Right, so you could include in this the roads, airports, and so on, yeah. All right, so let's move on now to I want to define a couple of concepts about the transport layer. So the first thing you're going to need to know is what a header is. So a header is just information attached to the top of a packet to include some sort of metadata about the packet. So it just indicates things like the destination, and the source. It can include other things, and as we go on, you'll see that actually headers can include many things. The TCP header, for instance, contains state about your connection and so on. But just for now, know that if we have some sort of payload, this is our payload, then the header is just something we attach to the top of it to include sort of things like destination information and the source of this packet, okay? So in our example here, can someone tell me what the header would be? So the answer is the information written on the envelope, and yeah, that's exact. So we have this envelope here, and we have to, and we have from, right? All right, so that's the header there. And then one more term is a segment. And this is just a transport layer chunk of data. Let's say a transport layer piece of the message. So if you have some sort of message that's this many bytes long, then a segment is just a part of that, okay? Something like that. And this terminology is only good for the transport layer. And as I mentioned earlier, in the network layer, we call this type of packet a datagram. All right, so I know it's confusing. There's lots of jargon there, but this is what everyone uses, so we have to follow that. Okay, and then I want to just emphasize a couple other points that, in our case, suppose that Canada Post is very reliable, but suppose that they weren't that reliable, and that they had delays. Like sometimes you'd have a week delay in sending your letters, or sometimes they would lose the letters. Then Ann and Bill here, our transport layer, they're constrained by the functionality of the network layer beneath them, right? So if, for instance, Canada Post is very slow delivering the messages, there's nothing that Ann and Bill can do about that, right? They're sitting on top of this layer, so they can't influence the network. They can only use its functionality. However, they can provide functionality on top of the network layer. So suppose that Canada Post loses something like 1 out of every 10 letters. Then how could Ann and Bill ensure reliable delivery of their messages? they could send two messages. I guess one's the actual message, and then one is saying, did you get that message? And if they don't receive a reply, then they keep sending the message again until they receive a reply. Okay, so that's one way they could ensure reliable delivery over this unreliable network. All right, and in general, we say that the network provides best effort service. Meaning that the network will try really hard to deliver your message for you. However, it doesn't make any sort of guarantees. It may lose your message, it may be delayed for a very long time. If you send multiple messages one after another, they may come in different orderings, and so on. And that's because the network layer only provides these best effort guarantees, all right? It is not a guaranteed service. It's not like, so in telephone networks, if you and I have an established call between us, then we have guaranteed quality of service for the duration of that call. I mean, your call can get dropped and things like this, but the number of bytes per second that you're allocated in that call remains fixed, whereas on the internet, you have no such guarantees, all right? You only have this best effort guarantee. And then just to go over one more point on our protocol here, on our transport protocol. Suppose that Ann and Bill, they left town for a while. They went to summer camp or something. And so they're gone. And then the other 11 children still want to exchange letters, so now they need a new transport layer. So suppose they ask, okay, the next oldest child in each household to be in charge of handing out these letters and so on. Well, suppose these kids are younger so that they lose more of the messages, and sometimes they are delayed. They get the stack of letters from the other kids, but then they wait a few days before dropping them in the mailbox and so on. So we can actually have different guarantees from different transport layer protocols, all right? And this is one thing that we'll see very clearly in our differentiation between UDP, which we'll cover today, and then TCP, which we'll cover for the next couple of lectures. So just let me write down exactly what I mean by that. And that is that the transport layer can provide certain services. And these services are, as I sort of mentioned, one service they can provide is reliable delivery. So they can provide this reliable delivery even over a unreliable channel, such as the internet. And they can provide flow control. Now, what flow control means is that it allows you to control the flow so you never overwhelm either of the endpoints. So you can imagine a situation where suppose we have this powerful server in a data center, okay? And it's sending data to your smartphone. All right, this server is many times more powerful than your smartphone. So it could easily overwhelm your smartphone with data. So flow control prevents that from happening, okay? It negotiates the rates of the endpoints so neither of them overpowers the other one, all right? And then a related concept is congestion control. So congestion control handles a similar scenario, except in flow control you can think of the congestion is at the endpoints, but in congestion control the congestion is in the middle of the network. So suppose we have a scenario like this, where we have 4 PCs, each sending to another one, and somewhere in their paths they share a link here, okay? So this link's shared. Now ideally, each of these, so let's say the flows are going this way. Each of these servers or users or whatever they are, each of these PCs should get half the bandwidth of this channel, right? If, let's say, the bandwidth of this is 1, then they should each get half of the capacity. And this is what congestion control provides, because without congestion control, they could easily overwhelm this link, and then no one could send messages through. Okay, if they're both overloading this. All right, so the question is that him and his roommate are sharing a network connection, right? And your roommate overpowers you with his, I guess, BitTorrent or something. Right, so we'll go into not all transport layer protocols provide congestion control. So in particular, if his application is using UDP, then there is no congestion control, so he can definitely take your bandwidth. Yeah, so the question is, in peer-to-peer, you can set your download and upload speed. That's not to ensure congestion control. That's just to ensure it's sort of fairness amongst humans. Like if you have multiple roommates, for instance, you may not want to set your BitTorrent client to use all of your bandwidth, things like that. But that's at the application layer. So applications can also do some sorts of congestion control, okay? But primarily that functionality is in the transport layer. Okay. So let's take a quick break now. All right. So now we're going to talk about how to multiplex and demultiplex. So if you're in engineering, you should have heard these terms before. For those of you who are not, they're pretty simple concepts, so we'll now introduce that. So a multiplexer and a demultiplexer is typically drawn like this, and this is what it does. So you have a bunch of incoming signals. I'll draw these with different colors. So let's suppose that we have these 4 different incoming signals, the green, yellow, pink one, and white. And it multiplexes these onto the same outgoing channel. All right, so now there's many different ways you can do this. You could do something like vary them in time, like I'm doing here. Or you can, in optical networks, for instance, you can use different wavelengths to multiplex them across a single channel. But the basic idea is that in multiplexing, so multiplexing goes this way. In multiplexing, you take many signals and place them onto one medium. Signals or transmissions, or however you want to describe that, many signals onto one medium or one channel. And then demultiplexing goes the other way. And so demultiplexing takes these multiple signals sharing a channel, and it turns them, separates them. So, separates. All right, so the concept is pretty simple. And let's see how this works in the transport layer. So now recall that we have these applications sitting on top of our transport layer. And suppose that we have a bunch of different applications running that are all using the internet. So for instance, this may be a web browser, this could be like AIM, some sort of instant messaging, this might be Skype, and this might be like Pandora or some sort of streaming radio service, okay? So you have all these, and now we need to combine all their flows into our one. We only have one network interface on most computers. So we need to combine those into the same network interface. So the way it works is that we have this multiplexer and demultiplexer sitting across the application and transport layers to translate from these applications down to the transport layer. Okay. Now, we need some way to be able to differentiate these flows from different applications, right? Like if this web browser sends a message and it receives a reply, we want the reply to go to the web browser. We don't want it to go to any other application, right? So the way we do this is we use these things called ports. And a port provides a unique identifier of applications on the end host. So this means that each application has a port number associated with it. And so just to give you some more details on a port, these ports are 16 bits. So that means that there's 2 to the 16th available ports for use. The ports 0 through 1023 are reserved. And these are reserved for well-known services. So reserved for well-known services. And we'll give you a couple examples just a sec. Well-known services or applications. For example, port 80. Does anybody know what port 80 is used for? HTTP. Yeah. And another example is just 21 is FTP. There's assignments for many different applications. You can look those up online. It's maybe not so interesting to have them all memorized, but knowing the concept and knowing how to look them up and so on is important. Right, so the question is, does the OS assign these ports? Yes, so when you open up a new socket, your socket's assigned a random port. Okay, from the upper, it will have at least 5 digits. Okay. So let's look at how this works in practice. So if we have a user here, let's just say user A, and we have user B, and then somewhere in a data center somewhere, we have a server. Let's just call this C. And A wants to request a web page from this server. All right, so it sends a segment with the following info. It's going to send it, it'll include its source port. It'll include the destination port. And then it has to include the source IP and the destination IP. Right, so when this user's web browser opened up this socket to this server, it got a random source port. So it'll get something like, let's just say 26.32.1. So it gets some random large number like that. And then the destination port, because this is a web page it's requesting, the destination port is 80. All right. Then its source IP is A, and the destination IP is C. All right. So now, similarly, if B requests a packet from the server, or excuse me, sorry, if B wants to talk to the server, then it sends a packet that looks almost identical, except this source port will be different and the source IP will be different. However, the destination fields will remain the same, right? And now let's say that the web server replies to B. So it replies with a packet whose header looks something like this. The source port is whatever random, or sorry, the source port is the source port of server C. So this is source port is 80. The destination port is the port that B used when it opened up this socket to server C. So let's just say that that was 33.111. And then the source IP is the IP of the server, so it's C. And the destination IP is B. So the question is, you can transmit and receive on the same port? Yes, you can. Yeah. Why doesn't A use 80 as its source port? It's because this 80 is reserved for incoming HTTP requests. Okay. All right. So I didn't show this part, but when it sent the request, that's the port that it put in there. So let me fill that in. Here's the source port. Is the 33.111. So the server knows to reply on that same port. The 80 is reserved for listening, for like web servers, okay? Because, you know, in theory at least, and more so in the early days of the internet, this user might have also had a web server running. And so you don't want to you have to use that port for outgoing requests, okay? Why is the server replying with the port 80? And that's because the connection's already been established. Yeah, I mean, once the connection's already been established, then it can use that port. And I mean, so it does have the additional difficulty then that both these requests are arriving on port 80, so it has to be able to distinguish between the clients, but it can do that using their source info, using their IP and their port. It's just this multiplexing and demultiplexing is sort of this shim layer between the two to do this multiplexing and demultiplexing for the applications to the transport, okay? But the transport protocols, you could have, let me draw my picture like this. You could have, this could give these to multiple transport layer protocols, okay? This could be like TCP, this could be UDP, for instance. All right, so the question is, for different protocols, does the demultiplexing and multiplexing happen simultaneously? So there's actually, as part of the transport layer protocol, it has to define its own multiplexing and demultiplexing. So in the implementation, you would see actually you would see different code running to do different demultiplexing. So now let's move on to talk about UDP. All right, so UDP stands for the User Datagram Protocol. Now I know this is quite confusing. The name of this is actually fairly confusing because if you remember, I told you these datagrams work at the network layer, but in the olden terminology, they used to use datagram for the network and the transport protocol. So when it was originally named back in the 70s, it got this name, the User Datagram Protocol, okay? But you probably don't actually really even need to know what it stands for, just know the acronym, all right, the UDP. So the goal of UDP is to be as simple of a transport layer protocol as possible, okay? As simple transport as possible. Now, what do I mean by as simple as possible? If you recall the services I talked about earlier that the transport layer could provide, I said it could provide things like reliability, flow control, congestion control, and so on. Well, UDP doesn't provide any of that stuff. Right? All it provides is the ability to make these end-to-end logical connections. Right? It doesn't give you any sort of niceness like reliability. So it's a connectionless protocol. And what I mean by connectionless is I mean that as soon as an application has data that's passed to the transport layer, so as soon as there's data to send, as soon as there's data, we send it. Okay. You'll see, we will talk about this protocol called TCP, and you'll see that TCP doesn't do that. Before it sends anything, it establishes a connection between the end hosts. But UDP doesn't do anything like that. As soon as there's data, it just says, okay, I know the source port for this, the source IP, and it sends it. All right? All right, so far we've talked about how UDP is this connection-less oriented protocol, and its goal is to provide transport but be as simple as possible. So now I talked about in the transport layer adds a header onto each segment to indicate where it's going and where it's from. So let's look at what the UDP header looks like. It turns out it's absolutely as simple as you can make it. So a UDP segment has a header. Let's try like this. This is the data of the segment. In other words, what it's actually trying to transfer. And then this part is the header. And each of these columns here is 16 bits wide. So the first field is the source port. And this is actually optional. Meaning that if you don't want to, you don't have to include that. Then the next field is the destination port. This is required because the receiver needs to know what port an application is listening on in order to handle the packet. Then the next field is the length. And this indicates how much data is in the segment's payload. Okay, so this is the length of the data. And then the next field is this thing called a checksum. And for IPv4, this is optional. Now, if you don't know the difference between IPv4 and IPv6, that's fine. You will get into these details later on. Just for now, know that this checksum is optional, at least in IPv4. And now what a checksum does is it's a few extra bits onto the packet to be able to detect if it was corrupted or changed during transmission. All right, so this is error detection. Meaning that if a few bits, if some number of bits are corrupted, then the transport layer can identify this. In our case, I guess the transport protocol is UDP. All right, now I'm not going to get into how these checksums work. We may cover this later in class, but for now, you just need to know that they provide some error detection facilities, all right? Why doesn't it include the destination address? All right, it's because that is in the network layer header. All right, so we actually have a header for each of these different layers. So on top of this, let me just erase this. On top of this, we'll do this thing called encapsulation, where you add another header, and this will be the network layer header. And the network layer is actually responsible for delivering to your destination. And so it's the thing that includes the destination IP, okay? So when in the next after, we're going to talk about transport for 2 weeks, but after that you'll learn about the network layer and about what this header looks like, all right? So the question is, there's some sort of reliability because there's this checksum. No, because in UDP, actually if it computes that the checksum is wrong, it just drops the packet, all right? It's just used to, be able to tell if you're handing the application, junk data or not, to make it a little nicer for the application. All right. I mean, UDP is really simple. This is all there is to it. As soon as an application has data to pass, it does a write to the socket. The socket multiplexes it down based on the port to this UDP. This UDP adds this very small header here and then writes it out, hands it down to the network layer, okay? So let's talk about some of the things that UDP doesn't have. So UDP does not have, now if you remember the things I talked about, it doesn't have reliability. It doesn't guarantee in-order delivery. All right. It doesn't do flow control, and it doesn't do congestion control. All right. So now we will talk about TCP in depth next time, but just to compare it to TCP, which TCP is the Transmission Control Protocol. It was actually created in 1974 by Vint Cerf and Kahn at UCLA, and they won a Turing Award for their development at TCP, which is sort of like the Nobel Prize of computer science. It's a pretty big deal because basically almost all traffic in the internet today runs over TCP. All right, and that's because UDP doesn't provide these things, and these are really nice if you're writing an application, right? Whereas TCP provides all of these, handles all of these, and in achieving these, however, it's a very complicated protocol. Which is why we'll spend about 2.5 classes covering TCP. All right, it's actually quite complicated, and I feel it's actually really interesting, pretty cool how they achieve these things over a medium where it's an unreliable network, and the network doesn't give you any sort of information about congestion control or flow control, except that if a link is overloaded, then the packet's dropped. So that's the only sort of information you have about congestion in the network, and based on that, you have to be able to do some sort of congestion control. Before we get into that, though, I just want to talk about, well, why would you actually use UDP? Are there any applications that you would want to use it for? So it's faster. Now, what do you mean by it's like faster? Right, so the answer is basically that it doesn't do these things like error checking, and it doesn't put your packets in the correct order for you. So as soon as you receive a packet, your application gets it. right? Whereas in TCP, it could be buffered for a little while, or it might not even be sent immediately. So let me just add on to this and say that it's faster in that you get fine-grained control. And what I mean by this fine-grained control is that with TCP, once you, in your application, you do the socket.write call, that data is immediately sent out on the network. Okay, with a more complicated protocol like TCP, it's not necessarily sent immediately. It could be buffered for a little bit, or TCP might be doing some sort of congestion control, so it's waiting because of that. But with UDP, as soon as you call, you say, send this data, it does send it. All right, so that gives you fine-grained control, which is useful for things like real-time applications. All right, so you're saying that it's useful for applications where these don't matter, which I agree with, but I'm not sure. I think they do matter in peer-to-peer. Okay, so it definitely could be used for some sort of peer-to-peer because, right, you don't necessarily, you're going to have to do some sort of reliability at the application layer anyways to check you have all the chunks and everything. So you don't necessarily need that. The in-order delivery you don't need. Now the flow control and congestion control, I'd say, are very important. And the reason why is because if it didn't have congestion control, peer-to-peer would be overloading, your ISP's network. Like, everyone would be using peer-to-peer. Rogers would have their networks would be saturated with this because no one would be doing any sort of congestion control. So Rogers would hate it and they would shut it down immediately. Right? So that's why some sort of congestion control in general, like internet-wide applications, is really very important. Because if your application ever gains, a large enough user base, then ISPs are going to start hating you. All right? All right, so yeah, so for things where you don't need reliability, it's good. Another advantage is that there's no connection establishment. So if I'm an end host and I have data to send to a server, I just send it. I don't establish a connection first. And so this is good for things like real-time applications as well, other sort of performance-intensive applications. Also, there's no connection state. And so without this connection state, there's less overhead. You can imagine if a web server is serving, say it's serving 1,000 clients, all with TCP, then it has to maintain state on each of those clients. Okay? And that becomes quite a bit of overhead and so on. And we'll see exactly in the next lecture exactly what sort of state is kept. But it can be quite a bit of overhead, and TCP can actually use a fair bit of memory. Just fine-grained control meaning that whenever when you hit the write call, the data is sent immediately. All right, and when you read in data off your Ethernet wire or your Wi-Fi card or whatever, it's immediately handed to your application. Okay. Yeah. So real-time app like voice over IP is one where you're doing voice telephony types of things, video chatting. Now you could use it for things like laser surgery and that sort of uses. So the question, was going back to about Bo's games. So probably his game. All right, so I asked you guys this is a homework question, but your video. I didn't want to give you the example of video games, but video games tend to need high performance, right? So they tend to use UDP. Now, if his roommate's hogging the bandwidth with BitTorrent uses TCP. It should actually be responsive to the congestion. However, maybe one problem is if his roommate's BitTorrent client might have like 100 connections open at once. And because there's so many connections, they sort of can get more than their fair share of bandwidth. All right, this is a well-known problem with TCP. Yeah, I mean, I'm not sure exactly what protocols and stuff this game is using, but generally with UDP, you can, if you want to do something called a denial of service attack, where you just flood someone's network with so many requests that their network can't keep up. So for instance, you could shut down the campus network by doing this. Then you just set up a basic UDP application to flood packets everywhere possible, all right? Because it doesn't follow congestion control. Yeah, so the question is like, for voice over IP, don't most packets need to be in order? And yeah, most do need to be in order, and most will actually arrive in order. If you know, for instance, in your guys' homework assignment, you were pinging websites, and pings actually do use UDP. So they use ICMP, but then they go on top of UDP with that, and so most of those pings got through, right? Yeah, so most of them get through. So most of the time packets get through in the internet today. Which is why, so using UDP for video chatting and so on, most of your packets get through and you see most of the frames. If you drop for like a half second, it's not usually a big deal. Okay. Okay, so then one other reason you might want to use TCP is the small packet header overhead. So if you look at this header, it's very small. It's only 8 bytes. So we're not adding a whole lot of junk onto our data that we're sending. We only add the bare essentials, whereas TCP, the header is 20 bytes. So it's more than double. So if you have, say, a very slow, you know, like when the internet was first developed, people were using these very slow modems and so on. So those 20 bytes back then might have actually made a difference in your sending and receiving time. And even today, for these high performance applications, you can still get things out much faster, especially suppose you're using some sort of application that sends very frequent but small updates, like a video game that says, hey, I'm at X, Y, and Z coordinates, and those are the only 3, there's like 3 numbers that are part of the message, then having this low overhead in the header really matters because it can be a significant portion of the packet size, okay? All right, so then let's just go over what sort of transport a few different applications use. So we talked about email, and email uses the SMTP protocol, as you guys have learned about, and this typically uses TCP. All right, web is HTTP. Also typically uses TCP. Actually, also always uses TCP. File transfer. Protocols FTP. And it typically uses TCP. All right, because again, we want this reliable delivery and so on. However, remote file servers they use protocols like the network file system, NFS, which you don't need to know necessarily how this protocol works. It typically uses UDP. And the reason that these remote file servers typically use UDPs is for performance, and because generally the users of the file server are on the same network as the file server, and so they want to get you the data as fast as possible and not be constrained with the congestion control and so on. So streaming multimedia, these are typically proprietary protocols. An example is like Adobe has some streaming flash protocol, right? And this is a proprietary protocol that they use. These are typically UDP, although more and more they are moving to TCP. And the reason they're moving to TCP is just the congestion control. They don't like overloading people's networks. So for instance, YouTube today has moved to TCP. Okay. Voice over IP, as we talked about. This is also proprietary typically. An example would be Skype. They have a proprietary protocol. It's typically is UDP. And then things like network management. The protocol here is the SNMP, which stands for Simple Network Management Protocol. And SNMP is over UDP. Does anyone know why network management would go over UDP? So the reason is because we actually don't want the congestion control and the flow control functionality of TCP, because network management, you're doing this in times when, say, the network's not responding for some reason, or there's some, the network's overloaded, it's really congested, so you need to access your router to turn on, configure some things or open up some ports or something. And so at these times, you want to be able to get your request through, even if you have to, say, like try your request many times. You want to be able to get it through, and so that's why they use UDP for this. So this is the app protocol. For transport, there's two main internet protocols, TCP and UDP. There are other transport protocols that are used on things like local networks, and in things like data centers, they now have a thing called like data center TCP. And but whenever you're doing things across the internet, you will almost always use UDP or TCP. All right, so that's it for today.